Good. All right. I think we got that going. And you can see this whole board, right?
Yes.
Yeah, you can
Up to the line.
So should be good here in this space. All right. So logic, kind of ignore what we have here for a second. I'll rewrite over in that space over there. We're going to be doing logic and kind of give you a sense for what logic is. If you were to pick any high-level field, like something like biology, then biology is built, the foundations of biology we would call chemistry, right? In other words, if you pick any biological concept and you keep saying, but what's really happening, you get down to the nitty-gritty, you're eventually going to get down to the chemistry. So some biological fact might be something like the mitochondria are the powerhouse of the cell. They produce ATP. Okay, that's a biological fact. But then you say, okay, well, how exactly do they produce ATP? And then that's going to get you into chemistry. You're going to talk about the chemistry of what's called the electron transport chain. Whatever. And they say, well, it moves around an electron like this, building this thing called an ATP, that's how it does it. Well, how exactly does it move around that electric charge? Well, if you want to know that, then we have to talk about physics. And then, if you want to know anything about physics, all the things we talk about, like in the photon, for example, is just a mathematical model. Right? We talk about a photon as a wave. What's a wave? Something that has a frequency. That's going to be something that's defined in mathematics. So all your physics ultimately reduces to some sort of mathematical model. And then, the foundations of your math, which is what we're talking about, is going to be logic. So, in this class, we are doing logic. We're going to start from the foundations of logic, build it up, and we're going to end with, I don't know if we'll end with it. We'll for sure do an axiomatic development of set theory. And then set theory is the foundation for all fields of mathematics. Any field of mathematics can ultimately be reduced to set theory. So then we'll have a good foundation there. Now to get started with logic, there is a prereq, and it's called language. I can't talk to you, I can't communicate anything to you if there's not a common language. That's what every field presupposes. So everything presupposes that we have some sort of language, we can talk, we can communicate some way. Logic now, we have to build on top of language. We have to nitpick from language the things that are very precise, the best things we can use to communicate. That's what we're doing in logic. So, logic, we have to use language to talk about it, and now we're kind of put in this weird predicament. We know that language that we use is ambiguous. It's not often clear what exactly someone's saying. It's a problem. But when we build our rules of logic, we need them to be very clear, very concise. We need to know exactly what they mean. Is it possible to use something ambiguous to get something very rigorous, well-defined? And the answer is yes, we do this all the time. For example, language is very ambiguous, but think about the rules of chess. If I make a bad move to the rules of chess, if I make a bad move in chess, you know it's a bad move in chess. Even though I just used imperfect language to communicate to you the rules of chess. We can still understand clear, concise rules even using vague language. And that's what we'll be doing in logic. We're going to be coming up with the rules for basically deductively reasoning. What are the valid ways that we can infer some conclusion from some premises? Those are the rules of logic. So that's what we're going to be developing. It's going to start with, we need to rip from language those completely unambiguous pieces that we can get so that we can very clearly and concisely communicate. So that's where we're going to be starting. Now, a little bit of a historical note. If you want to, or maybe more for those of you who have already done some philosophy. In philosophy, that's why, if you go through Aristotle's Organon, his first book in the Organon is the Categories. And his Categories is doing an analysis of language. That's exactly what he's doing. He's saying, here's the way we use words. We use it like this, 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 this. Here's ways we can put them together in meaningful ways. Starts out with an analysis of language. And that's called Categories. And then he builds on that. From language, he builds logic. And that's his prior analytics. And then from logic, he builds the foundations of science.
Miss math?
No, I didn't miss math. That's what he did. Now, Euclid came along, And Euclid is one who connected logic to mathematics. And he said, actually, we kind of need to base this in this. He didn't do it very rigorously. That was done much later. But he got started. And then Galileo is one who came along and based this in this. And then, I don't know, whichever chemist came along and started getting this clear, and whoever came along and started getting this clear. But that's kind of historically how it was built. So, logic, it's at the foundation of every field. Any high-level field you pick, we could ultimately build this pyramid so it comes back down to logic. It's why in any class you're in, whether you're in an English class, a literature class, a history class, a biology class, it's perfectly valid to use logic. In fact, your teachers encourage you to do it. That's because it all presupposes it.
Yeah.
So that's what logic is. It's at the foundations of any systematic body of knowledge we have. It ultimately reduces to logic. We need to use logic to build up those things. We don't need to do that because we'll be going over what exactly deductive reasoning is. We don't need to give you just high-level intuition. Okay, so in logic, we're building on top of language. We are only interested in sentences that actually say anything, that actually say something. So we're not interested in questions. We're not interested in instructions. We're interested in sentences that actually say something. Sentences that are either true or false.
Yep.
That's part of language that we're going to care about.
Okay.
We're not going to analyze a statement like, why did Jack grow beans? That doesn't mean anything to us. Jack grew beans. That I know how to talk about. That's either true or false. Now we can start doing some analysis of that. Why did Jack grow beans? True or false? Can't really do any analysis of it. So we're going to be interested in statements. What's a statement? A statement is a sentence that is either true or false, but not both. That's what we care about in logic. Statements. Okay, notation. We typically use Greek letters like alpha and beta to represent statements. Example, which of the following are statements? Go back home. Statement? No. 2 times 2 equals 5.
Yes.
2 times 2 equals 5?
Yeah.
Yeah, it's a statement. It's a false statement, but still a statement. It's something that we can either call true or false. 2 times 2 is 4. Yes, statement. New York is a suburb of Los Angeles. It is, I've been there. Went downtown Los Angeles and whoop, New York.
Here we go.
No, it was out in the suburbs. Okay, still yes, a statement. Thursday up tar paper. No, that's nonsense. The silliness of speedily. No, that's nonsense. I am the most beautiful girl in town.
Absolutely.
Yes, for sure.
For sure, that's a statement.
Yep.
It's either true or false.
You can take that one.
X plus 2 equals 5.
No.
Here's the weird one. No, this is not a statement.
Oh, yeah.
Right now, at this instant, we cannot call that true, we cannot call that false. We need an X to determine if it's true or false. We'll come back to these much later. That's one of the gotcha.
What are they called again?
It's going to be called a predicate.
Predicate.
Yeah.
So, there'll be something that come up later, but just get you familiar with the types of statements we care about. Statements that actually, sentences that actually say something. Those are sentences we care about. Sentences that we can call true or false.
And that's generally just a language that 2 people can understand would be a statement, essentially.
Yeah, it doesn't matter that we happen to be using English, but you can develop logic with Latin just as well as you can develop it with Greek, just as well as you can develop it with English. It doesn't matter. And all the concepts that we talk about, there's going to be equivalent concepts in every language.
I'm just wondering, what's the fine line between complete garbage sentences that don't mean anything to anybody, or ones that...
We're not going to do an analysis of language and classifying statements and say, in order for it to be a sentence, it has to have a
That makes sense.
noun and a
I respect
verb, stuff like that. So we're going to rely on your intuition to some extent to determine whether it is or isn't. But know that logic doesn't care. Logic isn't classifying sentences. Is this a statement, yes or no? Logic doesn't care. It says, if you give me a statement, here's what I'll give you. It doesn't say that's a statement, that's not. It just says, if you give me a statement, here's what I guarantee you. Okay. So now, sentential connectives. Crucial that we wrap our head around what these things are. Not going away. Sentential connectives. These are the terms or phrases that can be connected onto a sentence in a meaningful way. Kind of vague. So let's nail down exactly what that means. Example, not and or Jack believes it is probably the case that if fill in some sentence, then fill in some sentence, if and only if, etc. Anything you can add on to a sentence and still have the sentence make sense still have it mean something, is what we mean by sentential connective.
Would it be like, would also be one?
Also, comma, yeah.
It doesn't really impact it.
Yeah, doesn't really add anything to it, but yeah. So, example. Let alpha be the statement, the sky is green. Let beta be the statement, 2 plus 2 is 4. And now let's consider some of these statements when we apply a sentential connective. So if I apply the sentential connective to alpha and beta, that gives me the new statement, the sky is green, and 2 plus 2 is 4. I just applied a sentential connective to two sentences, two statements. Another one. The sky is green or 2 plus 2 is 4. Does that still make sense? Is that still meaningful?
Yeah.
Then or was a valid sentential connective. If the sky is green, then 2 plus 2 is 4. Might sound weird, but that still is a perfectly meaningful sentence. We understand it. Jack believes the sky is green. Does that make sense?
Yeah, that does.
Yeah, that makes sense. It's a meaningful sentence. So Jack believes is a valid sentential connective. We could come up with infinitely many sentential connectives. Right?
Yes.
Yes. Here's another one. It is probably the case that 2 plus 2 equals 4. Does that make sense?
Yep.
That's a valid sentential connective. Pretty fast and loose with what a sentential connective is here. And you can come up with a bunch of them.
There's still a statement, right? Or does it make the statement sentential connectives? Or keep it as a statement?
Thank you. I'm going to accidentally use sentence and statement interchangeably here. From here on out, okay, we're in logic. All we care about are sentences that are statements. Sentences that we can call true or false. From here on out, you can assume you see a sentence, it's true or false. So when we're talking about sentential connectives, we're talking about things that you can call true or false and combining things on them.
How do you
So
call the
there's still
bottom?
statements.
How's the bottom one statement? I don't get
It is probably the case that 2 plus 2 is 4. Because it probably is a case that 2 plus 2 is 4.
that. Yeah, but that's just as much true as it's false, so it probably does.
Would it be kind of like an X, like a variable almost?
Okay, it's not a truth functional sentential connective.
Okay.
We'll get to that.
Okay.
So, yes, thank you. We took this, which was a statement, and we added a sentential connective to it, which now you're saying, how do we determine if that's true or false? Perfect. And that is kind of a dumb sentential connective. We don't really like that one.
Okay.
So, a sentential connective is just terms or phrases that can be connected onto sentences in meaningful ways. It doesn't have to maintain the truth or falsity of the statements.
So it doesn't have to leave a statement.
Right, so when it's all said and done, this does not have to be a statement. Although in English that would be classified as a statement, right?
What, wouldn't it be considered like a predicate in a language rather than?
We're not going to touch predicates for a bit.
Okay.
So, you got a sentence, anything you can add onto it, and if it still means something to you, it's still a meaningful sentence, then we accept it. Now, you already pointed out one of the problems, and we'll get to the problem that you pointed out. On the next slide. First, we'll do the conjunction, and then we'll talk about the difference. Okay, so we can construct new statements by combining existing statements. New York is a suburb of Los Angeles, and I am the most beautiful girl in town. We just barely combine two statements together using the sentential connective and. Okay, definition, conjunction. If alpha and beta are statements, the statement alpha and beta is called the conjunction of alpha and beta. You with me so far?
Yeah.
Now, there's one problem with what I just said. I just barely said if alpha and beta are statements, the statement alpha and beta. I'm calling this thing right here a statement. In other words, I'm claiming that this and here not only is a sentential connective, but now it's a sentential connective such that if that could be determined to be true or false, and that could be determined to be true or false, this whole thing can now be determined to be true or false.
Okay.
It's a special kind of sentential connective. It's not one that you're going to have the same issue with. Where you say, we can't tell if it's true or false anymore.
Yeah, you always will be.
You always will be in this case. We need to demonstrate that you always will be. I just claim that you always will be, but just saying it doesn't make it so. And so we need to demonstrate that that is in fact the case. Before we write the SAP notation, we write alpha and beta as alpha and beta. We're using that symbol a lot for and. Hopefully most of you are already used to that. Okay, so if we're going to say that this thing right here is a statement, we better know how to determine the truth or falsity of it. So we have two statements that we're working with, alpha and beta. And there's 4 possible combinations. I know alpha and beta are statements, so I know that each of them are either true or false. So my 4 possible combinations are true, 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 false, false, true, false, false. Now over here we have alpha and beta. We're claiming that that is in fact a statement. So I better be able to determine in each of these 4 possible cases if it's true or false. Otherwise it wouldn't be a statement because it's not always true or false. Okay, and we already have good intuition for this. If alpha is true and beta is true, then the statement alpha and beta is true. If alpha is true and beta is false, the statement alpha and beta is
False.
false. If alpha is false and beta is true, the statement alpha and beta is false. And if they're both false, then alpha and beta is false. Perfect. So that is how we would write out the truth value of alpha and beta. If I know the truth values of alpha and beta, I can determine the truth value of alpha and beta. Sorry. Language. Gotta just use it. Alright. So that's how we determine the truth or falsity of the statement alpha and beta. Now, what about other conjunctions like the word but? So let's pretend that alpha is a statement, I love you, and beta is a statement, I love your brother. Let's pretend that we make up some word over here for some symbol for but. So we're going to draw out alpha. We'll just write but. But beta. If I know that, if I love you is true and I love your brother is true, then the statement I love you and I love your brother is true. If the statement I love you is true and the statement I love your brother is true, then the statement I love you but I love your brother is?
How can you say?
Well, we're saying that's true and that's true, aren't we?
Kind of.
I love you but I love your brother. Are they saying that they love you?
Maybe.
Are they saying they are? Are they saying that they love your brother? They are, so we can't really call it anything but true. Right?
Okay.
Similarly, if I love you is false, and they say, I love you, but I love your brother, they lied, right?
Yeah.
Right? And if they love you, and they don't love your brother, so this one's false, and they say, I love you, but I love your brother, they lied, right? And if they don't love you or your brother, and they say, I love you, but I love your brother, they lied, right?
Yeah.
So we can't help, if we try and come up with a truth table for this word but, it's going to be identical to and, so yet there's no difference there. And yet, none of us want to say that these two statements say the same thing.
Because they don't.
I love you and I love your brother does not say the same thing as I love you but I love your brother.
So it could be and or.
No, logically, if you're going to break it down, they say the same thing. And yet they say something different. And that's why but is not a good candidate for a word to use in logic. Most language is inherently ambiguous. You can't nail down exactly what we mean by that word but. It's somehow implying that this is somehow connected to this and they're somehow affecting each other. You can't make that explicit what exactly that is, what exactly that means.
It's based off context.
And it's based off human intuition. And we all probably have slightly different interpretations of what exactly is being said here. We all know exactly what this says. Anytime you see and, everyone's agreed. This one we could have some conversation about. So a word like but is much better in a poem, and a word like and is much better in a math class. So we don't want this word but to be used when we're developing logic. It's an ambiguous word. To the extent that it means anything logically, it just means the same thing as and. But we know that it doesn't mean the same thing as and. So there's something ambiguous there, something that we just can't capture.
So just use and instead.
So we use and words like but, we don't use them.
Because logically it means the same thing.
It's not just that logically it means the same thing. It's that if we try to nail down what it means logically, we say it means this when we want to say it doesn't mean that. So we're getting like a weird contradiction with ourselves.
Gotcha.
So I can't tell you what exactly it is about but that we don't like, except for that it's ambiguous. And we don't want ambiguous words in our logic that we're building up. We're trying to shave away from language just those pieces that we care about. Just get the absolute minimum pieces that everyone is perfectly agreed about, and we're just going to work with those. We don't want any ambiguity.
Okay.
Okay, so that's why a word like but isn't allowed. Oops. So, same thing. In logic, we are only interested in the univocal parts of language. The parts of language that only have one interpretation. Uni there meaning one. Univocal, one interpretation. Okay. And now we're going to move on to the problem Chandler pointed out, which is some of those sentential connectives we talked about seem kind of dumb, to put it in kind of a blunt way. There seem to be some that were okay and other ones that were just dumb. We're obviously not going to be interested in all sentential connectives in this class. We're only interested in what are called truth functional sentential connectives. So let's nail down what a truth functional sentential connective is. That is a truth functional sentential connectives. Those are sentential connectives where the truth or falsity of the resulting statement can be completely determined from the truth or falsity of the component statements. In other words, if you tell me whether alpha is true or false, and you tell me whether beta is true or false, I can now completely determine if alpha and beta is true or false. That's what it means to be truth functional. The truth or falsity of this statement is just a function of the truth or falsity of these statements. If you know the truth or falsity of the component statements, you can completely determine the truth or falsity of this statement. That is a truth functional sentential connective. And so those are the ones we're going to care about. The ones where if you apply them to statements, then we can still talk about the truth or falsity of the resulting statement.
Okay.
Okay. Let's do some examples. Let alpha and beta be two statements. What are they? Who cares? Alpha could be the sky's green, beta could be 2 plus 2 is 4.
Okay.
Alright. Which connectives are truth functional? If I know that the sky is not green, can I determine whether or not Jack believes that the sky is green?
Not really.
No. So it's not truth functional. If I know that the sky is not green, can I determine that it is not true that the sky is green?
Yes.
Yes. That's truth functional.
Yeah, it's truth functional. If I know that the sky is green, can I determine it is not true that the sky is green?
Sure.
So if I know whether or not alpha is true, I can determine whether or not it is not true that alpha is true. Make sense?
Yeah.
Okay, so this right here, it is not true that is a truth functional sentential connective.
Good.
That's valid. All right, what about and? If I know alpha and I know beta, can I determine the truth or falsity of alpha and beta?
Yeah, you already proved that.
Yeah, and we already did that one explicitly up there. What about this? Say I know what beta is. In this case, beta is true. Let's pretend beta is a true statement. Do I know that it is probable that beta is true? No, let's be say the statement is, Donnie won the lottery. Does that mean it is probable that Donnie won the lottery?
If you did, then
It's not truth functional.
Right, just because you know a statement, do you know that it is probable that that statement? I don't know. Weird, not weird. He had one interpretation on it. Some other people would probably had some other interpretation on whether or not that was true. So it's ambiguous, not clear, we don't like it. So it is probable that is not a truth functional sentential connective. So we won't be using ones like that. We won't be using you. We liked you. We liked you. We won't be using you. Right?
Okay.
Okay. Now, if it's truth functional, we should always be able to construct a truth table for it. So if you're trying to construct a truth table for some sentential connective, and you're running into problems, it's probably not truth functional. Alright, next one. Disjunction. If alpha and beta are statements, true or false sentences, the statement alpha or beta is called the disjunction of alpha and beta. It is false if both alpha and beta are false, otherwise it is true. So we have alpha and beta right here. Now we're talking about, notice the notation we use, alpha or beta, we use the V. And by definition, alpha or beta is true. Oh wait, this says when it's false. It is false if both alpha and beta are false. So if both alpha and beta are false, it's false. Otherwise it's true. So we're saying it's true in this case, true in this case, true in this case. Now let's make it connect with our intuition. And we're in a little bit of trouble with the English language and the word or. In the English language, we unfortunately use or in two ways. The symbol comes from a Latin word vel, which is used only in one particular way. We use or in the English language. So that's where the V comes from. And so the way they mean it is the same way that we use or in this context. So let's make you understand. Here's what we call the inclusive or. I tell you that you must take physics or calculus to apply for my class. If you just take physics, can you apply for my class?
Yes.
If you just take calculus, can you apply for my class? If you take both physics and calculus, can you apply for my class?
Yeah.
Yeah. So here we're saying either this is true or this is true or they're both true. That's the inclusive or, that's the one like this. Now let's look at a different way we use or in the English language. Your waiter tells you that order comes with a side of salad or soup. You say, wonderful, I'll take both. No, that's not what they meant. They meant that you can either have the side salad and not the soup, or you can have the soup and not the side salad. And that is called the exclusive or. So there's these two types of ors. They're both perfectly valid, inclusive or, exclusive or. When we use the word or in logic, the English word or in logic, it's understood that we are using inclusive or. And if we ever want to use the exclusive or, then we would use XOR for exclusive or. Or the symbol we have for it is this symbol with a line through it. Now, we don't really need it to develop logic, so we won't bother using XOR, but it's a perfectly valid, truth functional, sentential connective, and we could use it if we wanted to.
Why do we not use it very often?
It's just, we can get what we want pretty easily with the standard 5. So,
It's very rare that I use it in any programming.
yeah, even in programming, probably use it a lot in designing circuits.
That's what's interesting is computers, and fundamentally, they use the XOR heavily.
Yeah, I would guess. I can't remember back to those days, but either way.
Yeah.
It's not one that's as easy for people to reason about, probably partly for historic reasons. We can still recreate it with our different logical operators. So we don't have to have it. We're not missing anything by not having it. We could include it if we wanted to, but from our perspective, it's just one more thing to memorize.
So it's mainly just because humans have a hard time understanding it.
Well, it's probably more because there wasn't a word that really meant that at the time that logic was being developed. Probably. I don't know. Okay. Note, we want to use the exclusive or.
You already said that.
Oh. Thank you. Did I skip 2?
Mm-hmm.
Yes. Okay. Negation, the next one. Negation. If alpha is a statement, the statement alpha is false is called the negation of alpha. We also say not alpha. We also say it is not the case that alpha. Those are different ways that we say out loud the statement when we see not alpha. So we write not alpha as not alpha, there's our not symbol. And it's a negation. Truth table for it. Alpha. Alpha only has 2 possible values. Since alpha is a statement, it can either be true or it can be false. If alpha is true, not alpha is false. If alpha is false, not alpha is true. Negation seems like pretty straightforward, but it's one that often trips us up. It's coming up with the negation of a statement. So let's do an example. Which of the following are negations of all swans are white? Some swans are black. Does that negate all swans are white?
No.
It could.
Yes.
It does.
Yeah.
All swans are white, some swans are black.
Yeah.
Those two negate each other.
Because
No!
No.
They don't?
All right.
No.
No. It's so easy to fall into this trap. Negation is trickier than you think. Remember, if alpha here if this is alpha, you're saying this could potentially be not alpha, and I'm saying no. Not alpha cannot be this if this is alpha. That's what we're saying.
Yeah, I see what you're saying now.
Why? Because if they are negations of each other, if this is true, this one has to be false. And if this one's true, this one has to be false. What if I lived in a world with all yellow swans? Is it true that all swans are white? No. Oh, then it must be the case that some swans are black.
That makes sense,
No. So these are not negations of each other. If it's a negation of it, if alpha is true, not alpha has to be false.
yeah. So does every statement only have one negation?
Every statement only has one negation. There's several English ways to write out that one negation, but it only has one negation. It has a lot of contrary statements. We would say that these are contrary statements. They can't both be true. That's not the same thing as a negation. All right, next one. At least one swan is black. That's a negation of this.
No.
No. We still live in a world with all yellow swans. Okay, some swans are not white. That's a negation of all swans are white.
Yes.
Yeah.
Yes. If we lived in a world with all yellow swans, then this is true. Some swans are not white. If we lived in a world with all white swans, okay, now this is true. If we lived in a world of all black swans, okay, now this is true. If we lived in a world of half and half white and black, okay, now this is true. One of them is always true, one of them is always false. There's a negation of each other. Impossible for it to be otherwise. Okay. Next, not all swans are white.
Yes.
No.
Yes.
It does negate.
That's the most straightforward one. All swans are white, put a not in front of it, not all swans are white. That negates it.
But what about changing the all to a sum? Don't you have to do
You're
that? with negating
overthinking what we
something?
talked about in the beginning class. We'll get to quantifiers in this class.
Okay.
But just think about setting up a universe in your head. Let's think about a universe where all swans are white. Is this true?
Yes.
Yeah.
Is this true?
No.
No. Okay. Let's think about a universe where they're half white, half black. Is this true? Is this true?
Yeah.
Yeah. Anytime this is going to be false, this is going to be true.
Okay. I see.
Anytime this is going to be true, this is going to be false.
Gotcha.
Okay. Last one. Every swan is not white.
No.
That negates this.
Yes.
It does. It's not negate.
Yes.
It's not the negate.
If we live in this world of all white swans, is this one true?
Yes.
Is this one false?
Yes.
Yes. But in yellow.
Okay, let's go to our yellow one. Is this one true?
No.
No.
Is this one true?
Yes.
Yes.
But it's
Let's think about it a little bit more.
But it's just some swans are white.
Well, just some swans are white. Is this
Oh,
true?
Yeah.
You were right to begin with, but I wondered if you had thought it through all the way.
I knew I was white because there's only one.
There were two.
There were two.
Well, those two say the exact same thing. Not all is some. You were explaining this at the very start of class.
Okay.
Not all is some, and it's all
No, they were
possible,
true.
but it's even not.
But yeah, want you to have to think these through because negation, it's one of those things that you understand it and then in a year it's going to get to you. And you have to rethink through it. It's one of those pitfalls that you can fall into over and over
I
again.
literally watched this in one of your videos just the other day, and I still missed it.
Negation is trickier than people think.
Yeah.
Okay. Next. Let's negate some of these statements. State the negation of each of the following. All men in Georgia are at least 6 feet tall.
Some men in Georgia are not 6 feet tall.
Wonderful.
Would you have to do like at least change that?
Yeah, we'll assume if you're more than 6 feet, then you're.
Equal to or greater than?
Yeah, I think what he said is fine. We won't be too nitpicky here. All students in France like geometry.
That's weird.
Same thing. Some students in France don't like geometry.
It's not no students in France like geometry.
You can say not all students.
It have to be some, but in this case, it's possible that it could be none.
Yeah, the negation.
Could be
All
some,
students
could
in
be
France
none.
like geometry. There's at least one poor kid in France who doesn't like geometry. That's a negation.
Very cool kid.
All right. Every rectangle is a square.
Some rectangles are not squares.
Right. There's some rectangle out there that's not a square. That's its negation. Every circle has a center.
Some circles are in the center.
There are some circles that don't have a
Don't
center.
have a center, yeah.
All right. Every pair of numbers, for every pair of numbers A and B, A plus B is equal to B plus A.
Okay. A plus B is not equal to B. Oh. I
There
didn't think of that.
exists a pair
pair of numbers,
There
A
we go.
and B, such that A plus B does not equal B plus A.
Perfect. There exists a pair of numbers such that A plus B is not equal to B plus A.
Thank you.
Some men play golf.
All men don't play golf.
All men don't play golf. Or no men play golf.
There
That's
we
what
go.
I'm saying. It could be both. I hate it.
No men play golf. All men don't play golf. Those both say the same thing. A no is really just a for all.
Yep.
It could mean some or none. That's
A
like
none
not.
is just a for all. It's a for all not. That's a none. There is at least one number x such that x plus 3 equals 7.
There's no number x such that x plus 3 equals 7.
Perfect. There is no number x such that x plus 3 equals 7. Good. Alright. Should we negate a conjunction?
Yay.
Alright, let's negate a conjunction. So we'll take some conjunction. Today is Monday and the weather is cold.
Today is Tuesday and the weather's warm.
At least one of those two statements are true. So we either know that today is Monday and the weather is cold, or today is Tuesday and the weather is warm.
Doesn't matter if today's
Today is not Monday or the weather is.
I didn't think about that.
Or the weather is not cold.
That
Not
works.
cold.
Today is not Monday, or the weather is not cold.
Oh,
Could
yeah.
I
Oh,
also say,
just put knots, bro.
does warm work?
Just but not and switch the and to or.
Does warm work?
Or, that's right.
Negation and cold.
I don't know, is hot the same thing as warm?
Probably in my mind.
Well,
If warm is to you an at least thing, then sure.
I can see where that is.
But
ambiguous.
yeah, we won't care too much about nailing it down.
Okay.
As long as you get what's being said. All cats are black and all men are mortal.
Some cats are black, or some men are mortal.
Some cats are black or
Some cats are not black, right?
Oh yeah, some cats are not black, or some men are not mortal.
some men are immortal. Right.
Yes.
Perfect. Some rectangles are squares and some triangles are equilateral.
All rectangles are not squares, or all triangles are not equilateral.
Perfect. Right?
Now I'm getting it.
Hold on. You said all. Oh, okay. All triangles are not square.
Or
Or.
it's rectangles, but yeah.
What's so funny? I'm trying to figure it out.
You did what I did, where I say the wrong word.
He
Oh.
said triangles are squares.
Oh, did I?
Or rectangles.
Yeah.
Oh, rectangles. Okay.
So all rectangles are not squares,
Okay.
or all triangles are not equilateral. Alright. Some widgets are gadgets and no wiggles or waggles.
what?
Some widgets are gadgets and no wiggles or waggles.
All widgets are not gadgets,
Okay.
or some wiggles are not waggles.
Are wagons.
Are waggles.
Some wiggles are wiggles.
Oh yeah, because you're taking out the no.
Remember, no wiggles or waggles is saying every wiggle is not a waggle.
Yeah.
And so when you negate that, you're saying some wiggles are waggles.
There we go.
Right? Remember, a no is really a for all not. Alright. And now, we got some good intuition for not alpha and beta is the same thing as not alpha or beta. Let's write that out just to make it clear. So we got alpha, we got beta. The four possible combinations are true, 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 false, false, true, false, false. Alright, so we're looking at alpha and beta, right?
Mm-hmm.
And then we're going to look at not alpha and beta. And then we'll just go straight to the catch.
Do we need not alpha and not beta?
Not alpha or not beta. Yeah, I was going to write them, but I'm running out of space and didn't want it.
Okay.
Alright? Now, let's do these. If alpha and beta are true, alpha and beta is
True.
true. True and false is
False.
false and true is
False.
false and false is
False.
wonderful. Now we're just going to negate this column. This is alpha and beta, so not alpha and beta is just going to be a negation of this. If alpha and beta is true, not alpha and beta is false. If alpha and beta is false, not alpha and beta is true. Right?
Yeah.
Okay. Now this one, we're going to have to really stretch our brains here. We're doing not alpha or not beta. So false or false is
False.
false. Wonderful. False or true is
True.
True.
true. True or false is
True.
and true or true is
True.
true. I notice that they give you the exact same thing.
Gotcha.
Okay. And that's typically the way you show two statements are logically equivalent. Truth table. Okay. Negating a disjunction. Let's do that. Negate the disjunction. I will study hard or I will fail. I tell you, you will study harder, you will fail. And Jeremy tells me, no, I won't. What is he telling me?
You won't.
I will not study hard.
And I
will
pass.
And I will still pass.
Pass, yeah.
Yeah. I'm not going to study hard and I still won't fail. Right?
Okay.
So he's
Yeah.
saying not this and not this. That's how you
I see.
negate and or. Let's try the next one. Some will work or all will starve.
No one will work and
No.
some will not.
No, is it the negation of some all?
Yeah, but no.
Or not all, sorry, not all.
No, all is like no one. Right? No.
Am I confused?
What's the opposite of some will work?
Nobody.
All will not work.
I mean, could
If
not-
you
not-
tell, if anyone work for you anymore? Does Chandler still work for you? If Chandler comes to you and he says, some people are working at the job, and you find out he's lying, what did you find out?
No one's working at
No one's working at the job.
Okay.
Alright, what's the opposite of some will work? None will work. So, none will work, and
Some will not starve.
some will not starve. If everyone didn't starve, what do you know?
Okay, some will not start.
There's one sick cannibal.
Yes.
Right?
Okay.
Okay. Next one. Every triangle is isosceles, or every triangle is right.
Some triangles are not isosceles, and some triangles are not right. Did I get that?
That's
Does that mean-
true.
Okay.
What? That sounded right.
No, that's right.
Okay.
Thinking about interpretation of this sentence, I wouldn't have said anything otherwise, but just thinking about it, what they meant by the word. Doesn't matter. Yes, what you said is perfectly fine.
That
Okay.
philosophy.
No roses are red, or some violets are blue.
Some roses are red.
Or not red.
Oh yeah, some roses are not red.
I think you should take the note. Roses are red.
No roses are red. What's the opposite of that?
Roses are red.
Oh.
Some
Wait.
roses are red.
Some
Some
roses are red.
Okay, never mind.
How do I prove you wrong?
Yeah.
If you say no roses are red, how can I prove you wrong? I just need to show you one red rose.
Yeah.
So the opposite of no roses are red is some roses are red.
And
And
all violets are not blue?
all violets are not blue. Or no violets are blue.
Yeah. Oh. I
Right?
see it.
Okay, so let's go over what we just did there. What we just read we're showing is not alpha or beta is logically equivalent to not alpha and not beta. So,
You can just like switch the symbols. Oh, yeah, switch.
I'll just gotta get rid of all these. Okay. Shoot.
Or.
This is an or.
Mhm.
This is an or. This is an and.
Yeah.
Okay. So let's go over it. True or true is?
True.
True. True or false is?
True.
False or true is?
True.
False or false is?
False.
Okay, now we negate this column. So that's going to give us false, 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 true. Now we're going to have this on our head. False and false is
False.
false. False and true is,
False.
true and false is,
False.
true and true is
True.
true. And they give us the exact same thing.
Okay.
Yay. All right. Not versus never. Here's another one that this is kind of like the and versus but.
Okay.
Two words are kind of saying the same thing, but then again, not really saying the same thing. If I were to tell you that the sky is not blue, I'm saying that it's true that the sky is not blue. You can conclude that, right?
Yep. True, false,
Yeah.
Right? If I tell you the sky is never blue, you can still conclude that the sky is not blue.
yeah.
Yeah.
So these
okay.
both kind of allow you to conclude the same thing. But are they saying the same thing?
Not
It
really.
was like,
Never.
it's never been blue before.
Never's affecting time.
Yeah, never somehow bringing time into this in a weird way, right?
Yeah.
It won't be anywhere in the past, it won't be anywhere in the future, it will never be blue. But we don't really have good definition for what time is here. Time, that's a physics concept. We're talking about logic. We can't introduce time into logic.
But we just assume that it means false,
Well, I'm saying that's the only way we can interpret
or
it.
that it means not.
So it's kind of like but. If we give some logical interpretation to the word but, we have to treat it like and. If we give some logical interpretation to the word never, we have to treat it like not. And yet, we intuitively know there's something different there.
Yeah.
So just give me another example of one of these words that we don't introduce into logic.
Okay.
Unless time is. Oh wait. Is time ever have anything to do with logic?
No.
Cool. Interesting.
Time has nothing to do with logic, time has nothing to do with math, time is a physics property.
Interesting.
Time and space, those are physics. Well, we talk about space a lot in math, but it's not this space.
Same as
It's just what we use to model this space.
space.
So we have mathematical models for these things, but the physical concept doesn't exist in math anywhere.
So we never talk about time and logic. Well, I guess we could. You know. Okay. Interesting.
Yeah, but time and space, those are properties of physics. And those are things you talk about in physics. Not so much in logic, not so much math.
If something, so you would. Okay. Interesting. I don't know.
In math, we can talk about the mathematical models that we use to model space and time, but that's not really the same thing as talking about space and time. Let's talk about the models that we use to represent space and time. The same way that talking about a wave and talking about photon aren't the same thing, even though we use waves to model photons. Never mind.
I think I get what you're saying.
All right, continuing. We'll have a lot more to say about proofs. I guess we can kind of introduce you to the concept here, but we'll have a ton to say about proofs. I'm just piggybacking on some slides I already had. That's why I'm doing this. All right, when we try to convince someone of the validity of some statement, we say, this is true because that is true. If they agree with the that, if they agree that the that is true, and they agree that this necessarily follows, then they will be convinced. How do you convince anyone of anything? You say, well, it's true because this other thing is true. And this other thing means that that thing has to be true. That's how we convince people.
That's
These types of arguments. We'll get down to exactly how we convince. I can give you the word now. We convince them with a tautological implication. And we'll have a lot to say about what a tautological implication is. And I really don't like the summary for this class. Logic can be summarized as a study of the rules for making correct statements.
Yes, we're.
Yeah, good enough for a discrete math class.
Yeah.
All right, proofs. Proofs always consist of a statement of the form, if so-and-so is true, then such and such is true. We can always rephrase proofs as an if-then statement. Showing that an if-then statement is always true is showing that it's a tautological implication. That's what means to prove something. Show it's a tautological implication. An example of an if-then statement, we'll do much more thorough proofs than this. This is not an example of a proof in this class. If 3x is equal to 4, then x is equal to 4/3. If a is equal to 2 and b is equal to 3, then a squared plus b squared is going to be, let's see, 2 squared is 4 plus 6 is 10. Yay. So all proofs are of this form. Everything you did in an algebra class, even if you didn't take the time to do it, it was something exactly like this.
Yeah.
Every time you're using an equation, you're saying this line implies this line implies this line implies this line, even though you don't explicitly say it. You're doing these proofs. So all mathematical proofs are of the form if alpha then beta. We call the alpha in these things the antecedent or the condition, and we call beta the consequent or the conclusion. Antecedent and consequent, or condition and conclusion. Those are usually paired together. Alright, so now let's jump into an implication proper. And now we got to the hard one.
Yep.
Implication. This one's always a beast. Alright, if alpha and beta are statements, then the statement alpha implies beta is called the implication. We also read this as if alpha then beta. We also read it as beta if alpha. We also read it as alpha only if beta. We also read it as alpha is a sufficient condition for beta. We also read it as beta is a necessary condition for alpha. And you will see all of those. So, got to get comfortable with each of these terminologies and see how you need to be able to read it in one of these forms and instantly be able to interpret it in your head as what is implying what. So, let's go through a few here and tell me what statement is implying what. Or in other words, say it in an if alpha then beta form. Because I think you all understand if it's if alpha then beta, it's alpha's implying beta, right?
Yep.
Right, so let's just state each of these in that form. If I eat strawberries, I get hives.
Then I get X.
Yeah.
Yeah,
I
it's just,
strawberries.
if I eat strawberries, then I get hives. Just left it there now. Nothing hard there. Alright. People who don't study mathematics don't have good sense.
If you don't study mathematics, then you don't have good sense.
Yeah.
If you don't study mathematics, then you don't have good sense.
It's an implication.
Or if you have good sense and you study mathematics.
Yeah.
Using contrapositive. But we'll come back to that. What you said is perfect. The crops will be saved if we have rain this week.
If we have rain this week, the crops will be saved.
Perfect. That's saying if we have rain this week, then the crops will be saved. This is the antecedent. This is the consequent. Right?
Okay.
Perfect. It will rain tomorrow only if it gets cold. Is that saying if it rains tomorrow, it will get cold? Or is that saying if it gets cold, it will rain tomorrow?
If it gets cold, it'll rain tomorrow.
If it gets cold, it will rain tomorrow, right?
Yes.
No, it's actually saying it the other way.
Yeah, if you
It's
were saying
saying-
if.
If it will rain tomorrow, then it got cold.
Yeah.
Now I know that your brain is bothered by that one. So I found examples that will make it crystal clear to your brain. And this one works great for our intuition. You'll agree with it, trust me. I say there is oxygen if there is fire. What does that mean?
If there's fire, then there's oxygen.
If there's fire, then there's oxygen. Now I'm going to say there is fire only if there is oxygen. What does that mean?
If there's oxygen, then there's fire.
Does it?
No.
Is it, think about it this way, is it true that there is fire only if there's oxygen? Is that true?
Yes.
Yes. Does oxygen imply there's fire, or does fire imply there's oxygen?
Fire implies there's oxygen.
Fire implies there's oxygen. Just because there's oxygen doesn't mean there's fire. So you can intuitively recognize that this is true. And we know that the way it works is fire implies oxygen. It is not the case that oxygen implies there's fire. If there's fire, then there's oxygen. That's a weird one.
So, that if messing me up.
It will throw you off. And the terrible thing about it is only if is one of the three most common ways an implication is phrased. So I've got to get comfortable with it. So when you say alpha only if beta, that means alpha implies beta. If you see alpha if beta, that means beta implies alpha.
Okay, so in the statement that it will rain tomorrow only if it gets cold, just because it gets cold doesn't mean it's going to rain. Is that what it's saying?
Right. It's saying if it did rain tomorrow, then that means it got cold.
Yeah, okay.
This being true means this is true.
And then our iteration flip that logic around saying, oh, well, maybe if it's cold, then it'll rain.
Right. So with these ones, Our intuition is often throws us astray with the only if.
Yeah.
So the fire and oxygen seems to make it crystal clear to our intuition, so I always throw that one on there. Alright, so that's some examples of stating implications a bunch of different ways.
Are we going to do a truth table for implications?
Oh yeah.
Okay.
Just getting comfortable with them. That's what all this is about. Example. Just understanding implications. Okay, we can do this. Example. What can you conclude given the following statements? What can you conclude if you know, so you know it's true that if Fred is on the team, he must go to bed early. Let's assume you know that.
Okay.
And then I tell you, Fred went to bed early. What can you conclude?
He's on the team.
Can you conclude he's on the team?
Yeah.
No.
No. If Fred is on the team, he must go to bed early. He went to bed early. Maybe he's depressed he didn't make it. Right?
Okay, yeah.
Okay. Now, let's assume that we know if Fred is on the team, he must go to bed early. And we know that Fred does not go to bed early.
He's
Not on the team.
Then he's for sure not on the team.
Okay.
Good? Let's do another one. If a man is a postman, he has foot trouble. Okay.
Occupational hazard.
And we also know that this man has perfect feet. What can we conclude?
You don't
He's
know
not a
that.
postman.
He's not a postman. If a man is a postman, he has foot trouble.
Oh my word.
And I know this man has perfect feet.
So he's
What
not
are
a postman.
perfect feet?
The feet on this man.
Sherlock Holmes is situation.
Name logic.
Non-troubled feet. That's what perfect feet are. All right. Now let's pretend we know this, and we know that that man has foot trouble.
Can't tell.
Doesn't. It could imply that he has a postman, but he's not. Doesn't.
Maybe he's a postman, maybe not. We don't know. It doesn't roll it out, right?
Yeah.
Okay, next one. You will be given a ticket only if you are a sophomore. Let's just make sure we understand this statement first before we move on.
Sophomore, then you'll be able to.
Does this mean if you're a sophomore, you'll be given a ticket? Or does this mean if you're given a ticket, you're a sophomore?
I have
If
no.
you're given a ticket yourself.
It means if you're given a ticket, you must have been a sophomore. Because only sophomores were given tickets,
Yeah.
right? Maybe some sophomores were missed, but the people we gave tickets to were only sophomores. You'll be given a ticket only if you're a sophomore. Make sense?
Yep.
Okay. Now we know Jean was given a ticket. What do we know?
She must be a sophomore.
She must be a sophomore
She's a sophomore.
How do you know it's the sheep?
I don't know.
because it's Jean.
Don't you know Jane, dude?
It's Jean.
She's a sophomore.
No, that's Jean. Talk to her.
Well, then-
All right.
It's getting talked to.
Let's say we know that George is a sophomore.
Assuming you're gendered.
Okay.
Did he get a ticket?
Yeah, you don't know.
Yeah, he got a ticket because we only gave tickets to sophomores.
No, he was homesick.
Yeah, maybe he was homesick. Maybe we ran out of tickets.
Yeah.
So everyone we gave a ticket to was a sophomore. Poor George got missed. All right, next. The house will burn down if we don't get water.
We don't get one.
All right? We do get water. Can we conclude?
That the house. No.
We can't. We don't know.
Yeah, you'd still be burning down.
Because
the
if
house.
we don't get water, then the house will burn. So
If we don't get water, the house will burn down. Okay, we got water.
nothing.
Yeah, we don't know anything. Right? If a house is burning down, you know that if you don't get water, the house will burn down. I bring you a bucket of water. I say, there you go.
Yeah,
You got water.
So I was gonna say bottle of water. Bottle of water. Solve the problem.
Right. One of the most dangerous things people in general, not the students, people in general do is this type of logic. They read the implication one way and then they use it the other way. Happens all the time. Let's do another one. We know that the house will burn down if we don't get water. And we also know that we didn't get some water.
I know for sure the house burned down.
For sure the house burned down. Okay. Next. Okay, one more thing before we do the truth table for implications. This I added in thinking it might help. Maybe not.
Okay.
When we have an if-then statement, this is not the same thing as if it was the case that da 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 da, then it would be the case that da 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 da. Those do not say the same thing.
Why not?
I'll give you an example.
Okay.
If there are 100 husbands in America, there is only one wife.
That's not how polygamy works.
If there are 100 husbands in America, then there is only one wife. Are there 100 husbands in America right now?
Yes.
There's at least 100. We don't know if there is
Oh,
exactly.
I meant exactly.
Okay.
Oh, no.
I meant in the exact sense. Pretend I put the word exactly in there. If there are exactly 100 husbands in America, then there is only one wife. Are there exactly 100 husbands in America?
No.
No. So is this statement false?
Yes.
Yes.
Is this vacuum?
You can't call it false. How can you prove me wrong? If there are exactly 100 husbands in America, there's one wife. You can't prove me wrong.
Oh, it's. Yeah. You're
You
right.
see?
Yeah.
Okay. On the other hand, if I would have said, if it was the case that there were only 100 husbands in America, then it would be the case that there is only one wife. You could now prove me wrong.
Yes, it's
You
not.
could go out there, you could get rid of all the husbands until there's only 100 of them, and get rid of all the wives until there's only one of them, and say, there you go, I proved you wrong. So this and this are not saying the same thing. This is saying, this is the state of the universe right now. This is saying, we get a fudge around. When we're talking about if then, we're talking about like this. We're not talking about like this.
Because the bottom one
That
is
makes a
9.
lot of sense.
Is that what you're saying?
Kind of. It's not truth functional, is what we would say.
True, you can't think of it like it. It's using time.
But yes, you can think about like somehow it's like time into the picture if you want, whatever. But yeah, this and this are not saying the same thing.
Okay.
You with me? So yeah, for those of you who've already seen vacuously true, this one's vacuously true. It'd also be like this. If 1's equal to 0, then I am the Pope. Prove me wrong.
Your purple dragon one is still the one I remember.
Yeah.
If Donnie's a purple dragon, there's a typewriter in the center of the sun. True. That's what we call vacuously true.
There it's good.
So what do we mean by vacuously true? An implication is vacuously true provided the antecedent cannot be satisfied. If it's impossible to satisfy the antecedent, there's no way to call the implication false. That's what it means for it to be vacuously true.
So if we were to say,
So this and this are vacuously true. Because it is impossible to satisfy the antecedent.
That's so weird.
It's one way you can say that is like it's impossible to prove that it's wrong, therefore it's vacuously true.
That's what we mean by it's vacuously true. It's impossible for you to prove that's wrong. Because how do you prove an implication wrong? You set up some scenario where the antecedent is true, but the conclusion is false. That's how you prove an implication wrong.
Am I going to be able to understand that by the end of this class?
No.
Vacuously true?
Yes.
I hope so.
Because as far as I'm concerned, until I can understand why, if something's false, something's not false and it's vacuously true. If something's not true, it's vacuously false.
Sometimes you can directly prove them. So this one we can actually directly prove if you want. I can actually prove to you in a way that would appeal to your intuition more that if 1's equal to 0, then I am the Pope. You ready?
Yeah.
I'll prove to you. Let's pretend that 1's equal to 0. I'll prove to you I'm the Pope.
Okay.
Alright. If 1 is equal to 0, add 1 to both sides. 2 is equal to 1.
Okay.
Right?
Yeah.
You with me so far?
Yeah.
The Pope and I are 2. Therefore, the Pope and I are 1. Therefore, I am the Pope.
Dude.
The Pope and I.
The Pope and I are 2. And since 2 is equal to 1, the Pope and I are 1. Therefore, I am the Pope.
That's true.
So I just really showed you. I just showed you if 1's equal to 0,
That makes so much sense.
then I am
That's
the
what you're
Pope. But 1 is not equal to 0, so this is an implication that is vacuously true.
The only thing I kind of understand about this whole thing is that there's actually like 3 booleans here. There's the if boolean, there's the then boolean, and then there's like the conjunction boolean kind of, if that makes sense.
Perfect. Yeah, so let's draw out the truth table now and do it. So we have alpha, we have beta, and then we have alpha implies beta. Right? 4 possible scenarios. We can have true, 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 false, false, true, false, false. This seems to always work better with concrete examples. I always want to do concrete examples for implication. Let's set it up. Alpha is going to be the statement, Donnie's holding blue chalk. Beta is going to be the statement, Donnie's holding red chalk, pink chalk. I set the scenario where I'm holding both. So now we're talking about this world view. Nothing can change now. This is the whole universe. Nothing else exists. Just me and these chalk. No time, no space, just me holding chalk, just like this. Okay. I tell you, so here's the scenario. Is it true that if Donnie's holding blue chalk, Donnie's holding pink chalk?
Yes.
Yes, that's true. Right? So that one's true. Okay, next scenario. Is it true that if Donnie's holding blue chalk, Donnie's holding pink chalk?
No, that's false.
Yeah, it's false.
Okay. Is it true, so I set up alpha's false, beta's true. Is it true that if Donnie's holding blue chalk, Donnie's holding pink chalk? Is it false that if I'm holding blue chalk, I'm holding pink chalk?
Look, I have been through this so many times. And I'm telling you, if it's like, well, if it's not false, then it's true. Okay, then why can't we just say, well, if it's not true, then it's false?
We can.
Okay, so it's vacuously true or false.
Not false is exactly what we mean by true. Not
What about
false
not
is true.
true?
Not true is false.
Okay, so it could be vacuously false or vacuously true.
No, it's vacuously true because it's not false.
In my opinion, it should be like undefined or null. It's so, you don't understand why there's even a point to it.
Is it true that 1 equals 0?
No. It's not.
Is it true that I'm the Pope?
No.
Is it true that if 1 equals 0, I am the Pope?
It's not. It's not either. It's not true and it's not false.
I just barely gave you a proof of that
It's
one.
like an undefined.
I just barely proved to you that if 1 equals 0, I'm the Pope.
If it proved to it, I mean, it would imply that it was true.
If 1 equals 0, then 2 equals 1. The Pope and I are 2. The Pope and I are 1. I am the Pope. Therefore, if 1 equals 0, I'm the Pope.
But because they're both false, then that's not the case.
It's not the case that 1 equals 0. And it's not the case that I'm the Pope.
Okay.
It is the case that if 1 equals 0, I am the Pope. That is the case. It's vacuously true. It's one that you just gotta think about until it clicks, it clicks. I don't know.
I don't know. And am I the only one that's just not getting this?
The way it appeals to my intuition is keep track of the fact that it's not false. Not false is true. If you get a Boolean and it's false and you not it, it's now true.
Right?
Not false is identical to true.
Yes.
That's what not false means. Because not is truth functional. So if you want to say it's not false, you just said it's true.
Okay. I can go along with that logic. So, and that's a part that I haven't added in. So I really appreciate that. Now,
Okay.
So it's not false that if 1 equals 0, that 1 equals 0. Wait, sorry. It is false that 1 equals 0, and it is false that you are the Pope. But I can't.
Is it false that if 1 equals 0, I'm the Pope? No, it's not false.
What if I say, is it true that if 1 equals 0, then you are the Pope?
So if you can accept that it's not false, that's the same thing as true.
I get that it's not false, but why did you construct the language in that way, not false? Why don't I just say, is it not true? Is it not true that if 1 equals 0, then you are the Pope?
It is true that if 1 equals 0, I am the phone.
Okay, why?
I gave you a little demo.
Ah. I'm sorry. It just could be either. I don't still get it.
Well, it's not true. It's
Okay.
It is.
You're about
or
to-
it's not false. It's true.
Your laptop's not plugged in.
Oh. Should have turned off my screen brightness. Didn't even think about that. Oops. Well, we'll see how far we get. Okay. Anyways, so if the antecedent is false, we always call the implication true.
Yep.
The antecedent is false, we always call the implication true. And we call it vacuously true. We weren't on that. We were on this. The converse of an implication. If we know, we call beta implies alpha the converse of alpha implies beta. Just a name. Okay? So we're not going to be doing anything with converse for a while. I don't know if that's too important. We can keep going. The book isn't going to spend too much time on that. Contrapositive, here's a super useful one. Even if the book doesn't spend time on it now, worth looking at now. The contrapositive of a statement. The contrapositive of alpha implies beta is not beta implies not alpha. Now these two are logically equivalent. So let's look at alpha, beta, not alpha, not beta. Alpha implies beta, and not beta implies not alpha. So let's do the truth tables for these and then make it appeal to our interest. And we can have true, 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 false, false, true, false, false. Okay, this is just going to be a negation of alpha. So if alpha is true, we do false. And if alpha is false, we do true. This is just going to be a negation of beta. It's going to be false, true, false, true. Okay, alpha implies beta now. True implies true is
True.
true. True implies false is
False.
false. False implies true is
True.
true, vacuously true. False implies false is true, vacuously true. If the antecedent is false, the implication is true. Now let's look at this one. This one's not beta implies not alpha. False implies false is
True.
true. True implies false is
False.
false implies true is
True.
true. Vacuously true. True implies true is
True.
true. So notice that they give you the exact same thing. And now hopefully I give you some statements of it. Example, state the converse and contrapositive of each statement. Let's just state the contrapositive of each statement.
If it's useful, if they're saying the same thing, why is the contrapositive useful?
It's just a different way to think about it. We do it all the time in math.
That's like simplifying or something like
So forget the converse, let's just focus on contrapositive here. Alright. This says if x is 3, then x squared equals 9.
Okay.
What would be the contrapositive?
If x squared does not equal 9, then x does not equal 3.
Perfect. If two lines intersect, then they are not parallel.
If two lines are not parallel, then
Two
they
lines
do
are
not intersect.
parallel.
Oh yeah. The not of not is nothing.
Right. If two lines are parallel, then they do not intersect.
There we go.
See how I'm saying the exact same thing?
Yep.
Next one. If food is sweet, then it has honey in it.
It
Doesn't
has-
have honey, it's not sweet.
If it doesn't have honey, it's not sweet. Because if it's sweet, it has honey. So if it doesn't have honey, it's not sweet.
Yep.
Alright, next. If there is no atmosphere on Mars, then there is no life on Mars.
Challenge accepted.
If there is life on Mars, then there is an atmosphere on Mars.
Perfect. Oxygen is a necessary condition for fire.
If there's fire, then there's oxygen. Oh.
If there's not oxygen.
If there's not fire, then there's not.
If there's not oxygen, there's no fire.
Perfect.
That's right. Yeah.
Good, good. Alright. Next, logical equivalence, which we're going to represent with IFF, who will explain that a little bit more. Observe that alpha if beta is the same thing as beta implies alpha.
Yeah.
I'll go to the store if I can borrow the car means my borrowing the car implies I'll go to the store. Right?
Mm-hmm.
Okay. And note that alpha only if beta is the same thing as alpha implies beta.
Yeah.
So alpha if beta means beta implies alpha. Alpha only if beta means alpha implies beta. So if I say alpha if and only if beta, that is saying beta implies alpha and alpha implies beta. Saying alpha implies beta and beta implies alpha. They both imply each other. That's what we mean by alpha if and only if beta. Since alpha if and only if beta is used so much, we often represent that with the double F if. Alpha if beta means alpha if and only if beta. Alright, logical equivalence then. We call two statements, alpha and beta, logically equivalent, provided that you have alpha if and only if beta. In other words, if alpha implies beta and beta implies alpha, then we call those two statements, then we call alpha and beta logically equivalent. We also call the actual statement, alpha if and only if beta, a biconditional or an equivalence.
Okay.
So that statement we call it biconditional. Why a biconditional? Because it's two conditionals in one. Or an equivalence. Notation. We write the statement alpha if and only if beta as alpha back and forth arrow beta. So alpha if and only if beta. We'll just throw that on right here. Alpha back and forth arrow beta. That's true when alpha implies beta and beta implies alpha.
Okay.
And it's false otherwise. So true implies true is
True.
and true implies true is,
True.
and those together and we get true. True implies false is,
False.
false implies true is,
True.
and those together and we get
False.
false. False implies true is,
True.
true implies false is,
False.
and them together and we get
False.
false implies false is,
True.
false implies false is,
True.
true and true is
True.
true. So notice that alpha is logically equivalent to beta only when alpha and beta have the same value. Alpha and beta have the same value? True. Alpha and beta have the same value? False. Alpha and beta have the same value? False. Alpha and beta have the same value? True.
Okay.
Alright. Precedents. You kind of get used to these and you probably already understood from context. But the precedents that we apply these operators in is not, then and, then or, then implies, then logical equivalence. And these are the 5 operators we'll be using.
Oh, you're saying we do that in that order?
Yeah, that's the order you apply them in. The same way that from basic arithmetic, you know, you do exponents and then multiplication and division and then addition and subtraction. Same type of thing.
Is the and or like multiplication and division?
And is like multiplication or is like addition.
So they're not.
And not is like negative.
Then what's the implies?
Well, not everything just converts to arithmetic.
So you have an instant.
Is
That's why I have instant.
isn't the if and only if implies just 2 of the implies?
It's 2 of the implies, but it's understood that you do this operator before this operator.
So aren't they the same operator? That's just a convenient way of writing it.
Well, we just come up with an agreement. We agree that we will always do all these before we start doing those.
Okay.
I mean, you can make an argument for why do we do the ands before the ors? Because someone wrote the list and now we're going to stick with it, so we all do it the same way. That's why.
Okay.
So, just convention. Alright, so when you see alpha implies beta is logically equivalent to not beta implies not alpha, that means, here's how we would apply the parentheses. So I've just taken this and applying parentheses. We do the alpha implies beta before we do the logical equivalence, and we do the not beta and the not alpha before we do the implication, before we do the equivalence. So that's how you'd apply the parentheses.
Okay.
Seems pretty natural.
Yeah.
Here's one, not as natural. Alpha or beta and not alpha. You can remember that we do the ands before the ors. This means alpha or beta and not alpha.
Yeah.
And I think you'll usually be able to interpret from context what I mean when I write a particular symbol. If you're ever confused, we can always make it clear. Okay, that's it for that. Phew, we got through that. Last thing we need to talk about is tautology. Just gonna write more stuff up here, but it's missing chords when I shut up.
Want these lights on?
Maybe, yeah, we can turn on these lights. I'm just thinking based off of time, if maybe that'd be a good place to end it. And start with the tautology next time.
Well, aren't those really easy to understand? Isn't it like it's always true?
Kind of. Tautologies are something that are going to be a lot more complicated in logic than you're used to in just regular speech.
Yeah.
Intuitively, yes, that's what a tautology means. Maybe we'll talk about it in high level, and then we'll start next week with a review of tautologies.
Okay.
Okay.
So, tautologies, intuitively speaking, is a statement that is always true. We're being a little bit fast and loose here. We'll be more precise next time. Let's give you the telltale example, or not telltale, typical example of a tautology. Alpha or not alpha. That's a tautology. Let's see how we know it's a tautology. So if I have some statement alpha, what are its possible values?
True
True or false?
True and false. If alpha is true, then true or false is
True.
true. If alpha is false, then false or true is
True.
true. So that would be an example of a tautology.
Yeah.
Let's do a slightly more complex tautology. Let's say we got two statements, P and Q. Just to switch it up a little bit here. P and Q are two statements. And we're going to look at P and Q implies P. What do you think? Is this a tautology, yes or no?
It is.
And then we'll also try out this one. Maybe we'll flip it. Let's do P implies P and Q. Or maybe we'll do P or Q on this one. And in case you need parentheses, it's parentheses there and parentheses here.
Okay, thanks.
Alright. So, which of those do you think are tautologies? Either of them, neither of them?
The first one.
First one. First
Because
one.
of vacuous is true.
I'm working on it.
This one you think is going to be a tautology. What about this one?
No.
No? So we think yes, no? Let's try it out. So true, 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 false, false, true, false, false. Those are all the possible combinations for P and Q, right?
Yep.
Alright, let's break it down. True and true is
True.
true. True implies true is
True.
true. So this one came out to true. Wonderful.
Pretty straightforward.
Let's try another one. True and false is
True.
False.
false. False implies anything is
False.
True.
true. Alright. False and true is
False.
false. False implies anything is
True.
true.
Oh, then false and false.
Yeah.
False and false is
False.
false. False implies anything is.
True.
Yay, you got it. Alright. Now let's see if this one's not tautology. True or true is
True.
true. True implies true is
True.
true. Next. True or false is
True.
true implies true is
True.
true.
Dang, we both touched.
Next. False or true is
True.
false implies true is
False.
True.
false.
I mean false, yes. True.
Ha! Got you to switch.
This is a little weird.
False or false is
False.
false implies false is
True.
true. Ah, it's a tautology. Okay, so everything I wrote there was tautologies. Surprise. So those are examples of tautologies, and those are examples of ways that you can classify them as
Why are they
tautologies.
useful in logic again?
Why are they useful in logic? So in logic, we are going to develop a rigorous notion of what exactly it means to prove. This is not going to be the fast and loose proofs that we do in like a math class. We're being crazy fast and loose. They're going to be very precise, very perfect. And what we are going to mean by a proof is we are going to demonstrate that it is a tautological implication. Remember, every theorem in mathematics can be stated as an if-then statement. We are going to demonstrate that every single everything we prove, we're going to demonstrate that it is a tautological implication.
So you're saying the if-then statement is always true?
Yes, the implication itself, alpha implies beta, we're going to show, in certain cases, depending on what the alpha and beta are, is always true.
Alpha implies alpha is always true.
Alpha implies alpha is always true. Not a very interesting one, but yes. So with this little structure, obviously it's not going to be the case, but our statements aren't just going to be alpha. Our statements are going to be something complex like this. Notice I gave you here 2 tautological implications.
Yeah.
So our mathematical statements aren't just going to be one little sentence. They're going to be some kinds of statements.
Okay.
And our mathematical statements are also always looking back all the way to the axioms. That's what you do when you develop a field of mathematics. You start with your axioms, and you assume that those are true. And then you see that this conjoined with this implies this.
Mm-hmm.
And you might see that this conjoined with this implies this. And then maybe this together with this implies some new statement.
Does that mean that all conversations essentially are built off of these axioms and a set of axioms between people?
No. Language is more fundamental than logic. Every systematic body of knowledge is built this exact way. If what you're talking about is a systematic body of knowledge, it is fundamentally built this way. It's an axiomatic system.
Okay.
Whether you're talking about mathematics, whether you're talking about some field of science, whatever it is. When you talk about, for example, classical mechanics, what are the 3 assumptions that we start with for basic classical mechanics, basic physics?
Law of inertia.
Law of inertia, yeah.
The
Or
law
no,
of
Newton's laws. Newton's laws.
Newton's laws.
There we go.
We call them laws. And so you have, our first assumption is Newton's, well, usually there's a 0th law, Newton's 0th law of motion.
And those are axioms.
Isn't inertia his
Those
second law of
are
motion?
axioms in classical mechanics. Huh?
Isn't inertia his second law of motion?
No, we derive some of that stuff. We prove some of that stuff to be true.
Yeah.
Inertia, an object in motion will stay in motion.
Oh, no. Sorry, that is one of them.
Yeah. Isn't that what inertia means?
Yeah.
Well, an object in motion will stay in motion. Unless acted upon by no force.
Okay. That's true what you're saying.
Well, is it true that's what inertia is?
Yeah.
You can say that. You're not giving a definition of inertia. You're stating a law.
That's what inertia was.
Inertia is that law.
No, inertia was something different. It had a weird mathematic equation to it.
Inertia is 3 zeros. Okay.
Newton's 3 laws of, well, we can say 4 laws of motion, even though he only said 3. The first law is,
Force equals mass times acceleration.
no, that's not one. Or that's not the first one. It is one.
Okay.
The first one says that forces can be modeled with vectors.
That's right.
So it's telling us how we can go from our real world to mathematical objects.
Yeah.
So force, what's force? I don't know, but we can model it with a vector, and that's what we do. So the first one says we can model forces with vectors. The second one says,
And I'll keep going. This will stay in motion.
no,
You're getting these mixed up.
no, you'll agree with me when I tell you what it is.
Then force equals mass
Someone
times
impress me.
acceleration.
This is the one that is the most misunderstood. There exists some reference frame, such that in that reference frame, if the net force acting on an object is 0, then the net acceleration of the object is 0.
What the heck?
Yeah. it's-
That is his first law.
I don't think.
Definition. We define such reference frames to be inertial reference frames.
First law.
This is what the first law, yeah, so this is 0. The first law
Oh,
gives us our
gotcha.
test for what we mean by an inertial reference frame.
Newton's second law, this literally says F equals
He
M.
said-
We're talking about the first law. The 0th was we can model forces with vectors, which
Right.
Newton
I
did
thought
not
it
say.
said 0 on the bottom.
Yeah, I thought he was going to bump too.
Oh, sorry. So 0th law, first law.
We do it 0 first.
Okay.
His first law is that there exists some reference frame,
Yeah.
such that in that reference frame, if the net force acting on the object is 0, the net acceleration of the object is 0. That's not something you can prove.
Okay.
There's no proof of that in physics. It's something we conclude from inductively reasoning.
Weird.
Yeah, it's a weird law.
You can't prove the laws.
Axioms.
They're axioms for the system, yeah.
Okay, that's just kind of neat.
But we validate them in different ways. You can't prove them. So we have to validate them with inductive reasoning. And then we use them to prove other things deductively.
Gotcha.
And then his second law, that's his most famous law,
Force equals mass times acceleration.
right?
Yeah.
F equals ma, assuming we're in an inertial reference frame.
So yeah.
So the second law only holds an inertial reference frame. The first law tells you what an inertial reference frame is. The second law only holds an inertial reference frame.
Here's his words for the first law. An object at rest remains in rest, and an object in motion remains in motion at constant speed in a straight line unless acted upon by an unbalanced force.
There's a lot of like
So
this.
it makes sense.
So his first law is inertia,
Right.
not reference
But-
frame.
Half of it is.
I don't know what you're reading.
NASA's Newton's first law of motion.
Okay. You need to read it in context. He's saying there is some reference frame such that this holds. And then we give a definition. That's what we mean by an inertial reference frame. Because if you Google what's an inertial reference frame, it's going to say a reference frame where Newton's first law holds.
Okay.
I'm telling you, the first law is one that is said so awful it hurts me. And for the longest time, I always thought the first law was just a special case of the second law. And I actually had a teacher tell me that once. This is not the case. This is not just a special case of this, because then why would you need it?
Yeah.
That makes sense.
This one is telling us there is an inertial reference frame, and we call it, there is some reference frame where this is the case, and that's what we mean by an inertial reference frame. So we get a definition from the first law. And then the second law only holds in an inertial reference frame.
Okay, what's your third law?
This third law is, the way it's typically said is for every action there's an equal and opposite reaction.
That's right.
There's only one I
But it's if object A exerts a force of F on object B, then object B exerts a force of negative F on object A,
Yeah.
where F is a vector.
Okay.
So they all reduce to mathematical statements. But anyways, so those are the axioms of classical mechanics. And now if you want to talk about gravity in that system, you'd have to introduce as another law, Newton's law of gravity. And now we can also talk about gravity in the system. Oh, if you want to talk about electricity and magnetism in the system as well, you need to introduce Coulomb's law for electromagnetic forces.
So,
But this is how every system, every body of knowledge is built out.
so what's an example of a language that does not build off of axioms?
English.
But take for instance, you and I, we have an agreement. We can't prove that two.
Those are symbols
So
representing
that
things.
the word and,
Sounds.
or I don't know.
Yeah.
I can't prove to you that the words mean what they mean, but we have an agreement that they mean that.
Right. Our understanding of language is not something provable.
Right. And so
Because we have to use language to create the concept of proof.
wouldn't those be axioms then?
No. We have to use language to we'll define what axioms are in logic. So you use logic to construct axiomatic systems.
Cool.
So we'll construct axiomatic systems.
Does logic itself start with axioms?
No, there are no axioms for propositional logic.
I thought you said that the oh, okay, I guess you didn't.
Not for propositional logic. There are no axioms for propositional logic. Doesn't make sense to have axioms for propositional logic.
Right?
We use propositional logic to construct axiomatic systems.
There we go.
So you can't use axioms to construct the system that you use to create axioms.
What about statements are true or false? Is that not an axiom?
No, it's not an axiom.
So that's just definition.
So what is logic like not provable then?
We will prove that propositional logic is provable, I think, in the sense that you mean provable. You can prove propositional logic has no contradictions, for
What's the
example.
difference between propositional logic and logic in general?
There's a lot of different logics. And there's more sound logics and then more risky logics.
I see.
Propositional logic is foundation to all logic.
Wow, great. Okay.
So if you go off into some weird system of logic, you'll still be using propositional logic. I don't know, there might be some weirdo doing some weird thing where they're not even using propositional logic. People get crazy with it.
Okay.
Like, I can't remember what mathematicians call themselves. There's some mathematicians out there who refuse to use. So we're going to eventually, in logic, prove that you can use proof by contradiction.
Yeah.
To prove logic.
Well, I'm going to prove that proof by contradiction is a valid way to prove things. We're going to come up with some justification for that. There's mathematicians out there who say, no, we reject the reasoning there, we won't accept it. And so as they do their proofs, they refuse to use proof by contradiction. And so what's a real easy proof when you use proof by contradiction? They go in these crazy roundabout ways to still prove it.
Meaning they can still prove it, it's just proof by contradiction.
We always prove the exact same things. All prove it using contradiction. And they'll go in these crazy roundabout ways to come at the exact same conclusion. So it doesn't seem to change anything whether you do or don't accept proof by contradiction.
Why would they not accept it if they haven't found a single case of it?
Because not finding a single case is not an argument.
That's true. It's not an argument. You're totally right.
So that doesn't mean anything to them.
But so you can't really prove that proof by contradiction is.
No, you can't prove proof by contradiction works. You can just reason your way to it. So we're going to be talking about how we reason to these things. Because next time we're going to be talking about how we justify a rule of logic as a valid rule of logic. And it's kind of a weird situation you get yourself in. You can't say it's a valid rule of logic because it logically follows. Because what you're explaining is how you know it logically follows. What do you mean by it logically follows? And we need to come up with a notion of that.
Yeah, I think they're called circular definitions or something like that.
Yeah, we need to make sure that we're not getting circular.
Yep.
And so we're going to have to talk about tautologies to do that. And what we mean by something is logically implied by something else. Talk about something called showing that every single sentential interpretation of the statement makes it true. That's what we mean by a tautology. So, we'll get to that.
It's tantology?
That's a U. A-U.
Oh, tautology.
Tautology.
Okay. Cool.
Anyways, yeah, we can end it there.
Okay.
Pick up with tautologies next time. Quick question for you guys. How do you want to do the homework problems in this class?
Homework.
I'm fine with us just skipping over them. I'm also fine with whenever we come across them, maybe we do a few in class. Do you guys want to do some problems?
I do want to do some problems.
You do want to do some
When
problems?
we did it last time, we didn't do a lot of problems, and it kind of hurt me more. Like, it's a lot better for me to do a bunch of problems. So I would like to do them in class. That'd be my goal.
What about the stand up and
That's what I'm talking about.
Yeah.
Oh, great. Cool.
Now,
But like maybe
don't worry about it. When your time comes, you'll know. And then as far as recording, you worry about that? Does that
No.
put fear in you? Do you want that recorded?
I mean, Jerry and I got up and read paragraphs.
Well, the majority of this is going to be for you. Yeah, that was awful. The majority of what we record is going to be you guys. I mean, it's not going to be like John Doe goes and watches these videos. So it's just a matter of what you want in the videos in case you want to go back and reference
I don't mind at all.
Some of those guys with comments.
it. They get to come after you, hurt your feelings.
Yeah, they could be mean.
You just gotta get rid of your dignity right now and then you have a problem.
The two guys commenting.
And it's really you guys just creating other
And
accounts.
it's really just Jeremy like, hey, where can I access this information?
China finds out that I'm learning.
All right. So
Your thing's still going. So, you know.
we can stop that.